Lesson 5.9 is all about complex numbers. Before we can talk about complex numbers, we need to find out what a complex number is. So, quick history lesson. Way back when, a man named René Descartes, and yes, he is French, that's why it's not Descartes, René wanted to solve this equation. 2x squared plus 2 equals 0. So, let's see if we can solve it. So we'd subtract 2 from both sides, and we would leave 2x squared equals negative 2. Divide both sides by 2, and we get x squared equals negative 1. And to solve from here, we'd take the square root of both sides, which would leave x equals the square root of negative 1. Now, up until now, we've been saying that anytime we have the square root of a negative number, that it is no real solution. And this is true that there's no real solution. Sorry, that should be a T, solution. But there are imaginary solutions to ones like this, and René was the first to discover what that is. René defined this number I, or kind of a variable, a letter, but I is essentially the square root of negative 1. Or the way that he had it proposed was I squared is negative 1. So we call it I because I kind of stands for imaginary. So now that we know that, that makes jokes like this super hilarious. We have 8, who is meeting his friends 2 and 3, says, "Hey guys, you want to meet my new friend?" And they say, "Sure, but where is he?" He says, "He's right here." They say they can't see him, which is super funny because apparently he's an imaginary friend. He's an imaginary number, square root of negative 1. Man, that's hilarious. So, using complex numbers, we know from before that anytime we have the square root of a number, we can break it up into different numbers that were multiplied up to that radicand. So, if we have the square root of negative 28, we can break that up into square root of negative 1 times the square root of 28, which we know from René, the square root of negative 1 is just I, and we can break square root of, so I'm going to use green on this one, square root of negative 28 as square root of 4 times the square root of 7, because 4 times 7 is 28. Now from here we can see that square root of 4 is actually 2. We keep our I, and the square root of 7 cannot be reduced anymore, so we leave it like this. Now, this is technically our final answer, but we don't want to say it in this form. This is considered bad math grammar. We always want our real number, the 2, out in front, because our real friends come first, our imaginary friends can come later. And our irrational friends, well, we'll get to them way, way after. So we have 2i square root of 7. This then is our final answer. Similarly, looking at b, we can split this up into square root of, actually I'm not going to use a whole big one like that, we'll just say square root of negative 1 times square root of 32 times square root of y cubed. Now again, like René said, the square root of negative 1 is I. We know that we can split up square root of 32 into square root of 16 times square root of 2, because 16 times 2 is 32. And square root of y cubed can be broken down into square root of y squared times square root of y. Now this is very helpful because square root of 16 we know is 4. And the square root of y squared is y. And we have to leave our I. Our square root of 2 does not reduce any, nor does our square root of y. So we have I times 4 times square root of 2 times y times the square root of y. So here we have square roots that are still together. Here we have our constant out front and our y. These are our real terms. So they need to be out in front here, 4y. Then our imaginary friend comes second, and our irrational friends come way later. So we would say our answer is 4yi times the square root of 2y. So that'd be our final answer there. Moving on to multiplying these imaginary numbers. Multiplying them will be just like multiplying if we had coefficients with variables, so like 3x times 2x. We would multiply coefficients together to get 6, and our variables together to get x squared. Well, we're going to use the same process here to determine that negative 3 times 2 is negative 6, and I times I is I squared. Again, like Renee told us, I squared is just going to be negative 1. So essentially we have negative 6 times negative 1, in which case that leaves us with 6. Moving on to B. Again, in this case we have two different radicals, and we want to split them up into numbers that we can deal with. So we can take our square root of negative 1 out of the square root of 12, which leaves us with square root of 12 times, again, we can take out the square root of negative 1 and the square root of 2. Now, in this case, we see the same term here, square root of negative 1 times the square root of negative 1. And anytime we have the square root of something times itself, we know that it's just the radicand back to normal. So square root of negative 1 times square root of negative 1 is just negative 1. Now, our square root of 12, we can break that down into square root of 6 and square root of 2, which is helpful because we have another square root of 2 over here. So we have to bring it down, but we see that they pair up. So in this case, our negative 1 stays there. Square root of 2 and square root of 2 multiply together to make a 2. And we still have our square root of 6. So in this case, we rewrite our final answer as negative 2, because negative 1 times 2 is negative 2, times the square root of 6. And that would be our final answer. Moving right along. We've got some good problems here on I, different powers of I. And before we go over these ones, I just want to explore some properties of I here. If we have I to the first power, we know anything to the first power is just itself, so it's just I. If we have I squared, remember Renee told us that's negative 1. If we have I to the third power, remember, I to the third power is the same as saying I squared times I to the first power, because power to power property, power times power is just addition, here and here. So we know that it's just I times a negative 1, in which case, get rid of all these, in which case negative 1 times I is just negative I to the fourth power, again, I want to get rid of these ones here actually. I to the fourth power, power times a power, would be the same as saying I squared times I squared, because 2 plus 2 is 4. So in this case, that would be the same as saying negative 1 times negative 1, which we know is just 1. I to the fifth power now, we know that I to the fifth power is going to be the same as I to the fourth power times I to the first power. Again, power times powers add, and 4 plus 1 is 5. Well, we know that 1 times anything is just itself. So 1 times I would just give us I again. Similarly, we can see that I to the sixth, if I get rid of these here, I to the 6th is the same as I to the 4th times I squared. Again, I to the 4th is 1, and 1 times anything, that I squared, is itself again. Doing this, we can determine again that I to the 7th would be 4 plus 3, so we'd have our negative I. And I to the 8th would be 4 plus 4, so 1 times 1, which is 1. And I to the 9th would be, I to the 9th is the same as saying I to the 4th times I to the 4th times I to the 1, because 4 plus 4 plus 1 is 9. We have I to the 4th is 1, times another I to the 4th is still 1, times I to the 1 just leaves us with I. Now at this point, you're probably noticing that there's a pattern here. And it goes I, negative 1, negative I, 1. Then repeats I, negative 1, negative I, 1. And will continue to do so forever, actually. This pattern will continue, and it comes at every group of 4. So every multiple of 4, we come back to 1, which means the next one would just give us I again. Which is helpful to see because that means that any multiple of I, or any power of I, we can just subtract a multiple of 4. So in this case, if we have I to the 35, the closest multiple of 4 to 35 would be 32, because 4 times 8 is 32. So we would have 35 minus 32 equals 3. So I to the 35 is essentially the same as saying I to the 3. And if we remember, I to the 1 is I to the 2 is negative 1, I to the 3 is negative I to the 4 is 1, so I to the 3 becomes a negative I. Looking at our second example, I to the 57th, well, 57, the next closest multiple of 4 would be 56, because 4 times, I think it's 14 would be 56. So we would take away 56 and be left with 1. So I to the 57 is the same as saying I to the 1, which we know from our table up here is just I. So in this example, we have I to the 64th. Well, 64 minus our next closest multiple of 4, if we have 4 times 16, is exactly 64. So we'd say 64 minus 64 is 0. So this would be the same as saying I to the 0th. Now, since we don't have one up here, we could say that it's 60 here, in which case we have 4. So it would be the same as I to the 4th. But remember, anything to the 0th is 1. And we also know that I to the 4th from our table is 1. So both ways work, either saying that it's the same as I to the 0th or I to the 4th. They both mean 1. So in this case, our final answer is just 1. In this one, we have I to the 42. Closest multiple of 4 is 40, because 4 times 10 equals 40. So 42 minus 40 is 2. So this is the same as saying I to the 2, which again we know from our table is negative 1. So this one is negative 1.